Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. We've explored the oscillating graphs of sine and cosine, watching them move up and down as we draw them. In the real world, the cyclic nature is everywhere, from the ebb and flow of ocean tides to the changing length of daylight, or even the gentle rise and fall of a Ferris-wheel seat. Today, we're going to dive into a couple of these real-world scenarios and model it using a sinusoidal function. We'll take it step by step, no shortcuts, so you can see just how these mathematical waves can help us understand the world around us. In this first problem, we want to model the water depth as a function of time. And we're given the following important information. We know that the low tide is at a depth of 2 meters. And we know that the high tide is 6 meters. And also, we know that it takes 6 hours to go from low tide to the next high tide. So for problems like these, what you want to do is you want to sketch a graph that models the situation first, before even thinking about what the function is going to be. So we're going to draw our axes. And the horizontal axis in this case is going to be t, which is time in hours. And then our vertical axis is going to be d, which is the depth in meters. So there's another piece of information that I haven't highlighted earlier, which is that it is currently high tide. So this tells us our starting point. When we say currently, we mean right now at time 0. And we know that high tide is 6 meters. So we're going to say that 6 is over here. So this will be 2, 4, 6. And currently it is high tide, which means we have a depth of 6 meters right now. So since we know that it takes 6 hours to go from low tide to the next high tide, that tells us it also takes 6 hours to go from current high tide to the next low tide. So we're going to label our horizontal axes as 1, 2, 3, 4, 5, and 6. So after 6 hours, when t is equal to 6, we're going to be at low tide, which is 2 meters. So that's going to be right over here. And then 6 hours after that, which would be at 12, so that'll be 7, 8, 9, 10, 11, 12. That's going to be our next high tide, which is 6 meters. So since our maximum happens at 6 and our minimum happens at 2, then that means our midline is going to be right in between these two, so that's going to be at 4. So let's use another color and draw our midline at 4. And now we can go ahead and plot our other important point, which is at t is equal to 3, which is halfway between our high tide and low tide. We're going to have our point right on the midline. And then similarly, the halfway point between our low tide and high tide, which happens at t equals 9, that is also going to be a point on the midline. And now we're ready to connect our dots and draw our wave. So it's going to look something like this. There we go. So now, looking at this graph here, we can go ahead and write down our important values, which are the A, the B, the P, and the Q. So A here is our amplitude, and that is going to be the distance from the midline to the max or the min. So in this case, that's going to be 2. The B here can be calculated using our period. So looking at our graph, we can see that going from high tide to the next high tide, that is going to be 1 full period. And that happens in 12 hours. So if our period is equal to 12, and we can calculate it as 2 pi over our b value, then that tells us our b value is equal to 2 pi over 12, which is pi over 6. So let's go ahead and put that in there. Our b value is pi over 6. And then our p value here is the phase shift. But that would depend on what function you're using. You can either pick sine or cosine. But looking at the graph, because we're starting at the highest point, that is actually the cosine function, because the cosine function starts at the maximum. So which means if we were to select the cosine function, then we are going to have a phase shift of 0. Next, the Q value is going to be the midline, which we've calculated above to be equal to 4. And now we're ready to put this all together and write down our function. So our function here is going to be d of t is equal to, it'll be our a value, which is 2, times our function, which we've selected cosine. And our b value here is pi over 6 multiplied by t. And since our p value is 0, that'll just be minus 0, which we don't need to write down. And then finally, we have plus q, so that'll be plus 4. So this would be the function that models the depth of the water in this particular question. Now, the next part of this problem is to use this model that we have generated. And we want to find the depth of the water 3 hours from now. So since right now is time 0, 3 hours from now means our t value is going to be equal to 3. So if we wish to find the depth of the water at t equals 3, all we need to do is substitute in the value 3 for t, which means we're calculating d of 3. And that is going to be equal to 2 times cosine of pi over 6 times 3 plus 4. So then we get this is 2 times cosine of pi over 2 plus 4. Now pi over 2 is one of those special axis angles. So we know that cosine of pi over 2 is actually equal to 0. So then we get this is equal to 2 times 0 plus 4, which means our answer here is equal to 4. And our unit here is going to be meters. So as you can see here, once you have the model, you can rely on the skills you picked up in this playlist to find the answer. Most notably, we're going to be using our special triangles, other special angles to solve these trig equations. Now the next problem, we are working with a Ferris wheel. And we're going to follow the exact same steps. We're going to highlight the important information in this question, and then we're going to draw a graph to model the situation. So our Ferris wheel here has a radius of 15 meters. And the platform is 2 meters off of the ground. It makes one complete revolution every 40 seconds. So now suppose a seat is at its lowest point at time 0. We want to find the function for the height, which is h of t, of the seat above ground in meters. So we're going to start the same way. We're going to draw our axes. And this time, our horizontal axis is going to be t, and our vertical axis is going to be h. So at time 0, the seat is at its lowest point. So seat is at its lowest point at time 0, meaning right now, our starting point is the lowest point. And since the platform is 2 meters off of the ground, that means right now, the height is going to be right at the platform, which is 2. Okay, so we're going to say 2, let's say that's around there. That'll be our 2. And that is going to be our starting point. Now, since one complete revolution takes 40 seconds, that means if we're starting at the lowest point, we're going to go once around in 40 seconds. So the next time we're going to be at the lowest point is going to be 40 seconds later. So we're going to say that 40 seconds is right over here. That'll be 10, 20, 30, 40. So that means at t equals 40, we're going to be at a height of 2 once more. Now, because this one full revolution takes 40 seconds, we know that that means our highest point is going to be achieved at t is equal to 20, which is halfway between 0 and 40. So now we need to find what that height is. Now, if the Ferris wheel has a radius of 15 meters, then that means the diameter of the Ferris wheel is going to be 30 meters. And since our lowest point is 2 meters off of the ground, then that means the highest point is going to be 32 meters off of the ground. So at t is equal to 20, we're going to be at a height of 32. So that'll be over here. So let's go ahead and plot that point. And just like earlier, if our maximum is 32 and our minimum is 2, then the midline is going to be halfway in between. So we can find that by adding our max and min and then dividing by 2. So this gives us 17. So let's go ahead and draw that. That's going to be somewhere here. And now halfway between our min and max, which is going to happen at t is equal to 10, we're going to be on the midline. And then halfway between our max and min, which means t is equal to 30, again, we're going to be on the midline. So connecting these dots in a wave is going to give us something that looks like this. So now the starting point of this graph doesn't match our sine or cosine function. But we can see that because this graph starts at the minimum, you can see it as a cosine function that's flipped upside down, right? Because the regular cosine function starts at the maximum. So if we flip it upside down, then that's going to be starting at the minimum, which means we can actually say that this is a negative cosine function. So let's write that here. This one is going to be a negative cosine function. So let's go ahead and write down our important values. So our a here, which is the amplitude, is equal to the difference between the maximum and the midline. So that is going to be 15. Our b value here, we can calculate it using our period. So looking at our graph, we can see that one full rotation happens after 40 seconds. So that means our period here is equal to 40. And that is equal to 2 pi over the b value. So solving for b is going to give us b is equal to pi over 20. Next, we have our p, which is the phase shift. But we actually don't have a phase shift here because all we've done is flip our cosine function upside down. So flipping it upside down just means our a value here, instead of being 15, is going to be negative 15. So which means our p here is 0. And then finally, our q value is just our midline, which is 17. So putting all this together, we get our function h of t is equal to negative 15 times cosine of pi over 20 times t plus 17. Now, just as a quick side note, we decided to use a negative cosine function here, but you can actually also use a sine function. So sine function starts at 0, or starts at the midline, and it increases to the maximum. Meaning, if we wanted to use a sine function, we would start at this point and then start going up. So that tells us if we were to use a sine function, then this graph that we have here is the sine function, but we have shifted it 10 units to the right. So if you decided to use a sine function, your p value here would be 10. And that would also be a valid solution. But here we decided to stick with our negative cosine function. So this is our h of t. For the next part of this question, we're going to use this function that we have created to prove that it takes the seat 20 seconds to reach its maximum height. Earlier, when we were drawing the function, we already said that it takes 20 seconds to reach there. But we're just going to double check using this function that we've created. So our max height, h of t, is equal to 32 meters. So we're going to set 32 is equal to our function, which is negative 15 cosine of pi over 20t plus 17. And then we're going to go ahead and solve for t. So subtracting 17 from both sides will give us 15 is equal to negative 15 times cosine of pi over 20 times t. Dividing both sides by negative 15 gives us negative 1 is equal to cosine of pi over 20 times t. Now imagine that this pi over 20t is equal to theta, so meaning we're doing substitution. So if we let theta be equal to pi over 20t, then really what we're doing is we're trying to solve negative 1 is equal to cos theta. Now using our original cosine graph, which looks something like this, we know that the first time the cosine function hits negative 1 happens at pi. So therefore, we have theta is equal to pi. And now we can go ahead and do our substitution back, which means we have pi is equal to pi over 20 times t. So therefore, t is equal to 20. So coming back here, we have t is equal to 20. And our units here would be seconds. So therefore, we have now used our function to prove that it takes 20 seconds for us to reach its maximum height. And now let's go ahead and do a quick recap of everything that we covered in this video. We went through a couple of real-life periodic behavior that can be modeled with sine or cosine. And the key steps to finding that particular function is to first identify the max, the min, the amplitude, and the midline. And then we want to identify the period, or in other words, how long it takes to complete one full cycle. And thirdly, we want to decide if we want to use sine or cosine to fit the starting point. And we also saw that either one works, it's just that one of them may be simpler than the other. And finally, don't forget about your special angles and triangles and how to solve trig equations because they still come up. And now it is your turn to give this a try. Can you come up with the function t of t to model this situation here, and then use it to predict the temperature at 9 a.m. Don't forget to leave your answer in the comments below, and let us know if you'd like to see more applications of trig functions in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.